Have you ever tried to take a picture of something that's moving super, super fast and it comes out as a total blur? Well, physicists have a very similar problem, except their subject is the universe itself, and their camera? It's a particle collider. Today, we're going to dig into a new research paper that's basically a masterclass in how to sharpen that cosmic focus to see what's really going on inside a particle collision. So how exactly are they doing this? How are they sharpening that cosmic camera? Well, here's our game plan for today. First, we're going to look at just how hard it is to even take a picture of a particle collision. Then we'll talk about the auto mode they've been using for a long time and why, it's just not sharp enough anymore. After that, we'll get into the new manual controls that are a total game changer, see what this new user manual from the research paper unlocks. And finally, we'll explore why a clearer picture could honestly change everything we think we know about the universe.
Okay, so let's get right into it. To really get why we need a better camera, we first have to appreciate what we're even trying to photograph. And believe me, this is not your average photo shoot. We're going deep inside some of the most complex, most powerful machines humanity has ever built.
I mean, that's really the fundamental question, isn't it? How on earth do you photograph a quark? We're talking about the building blocks of protons and neutrons. They're just unimaginably small, and they're in this constant chaotic dance. You can't just point a camera at them. So instead of a camera, what we do is we take particles, like protons, and we accelerate them to incredible, just mind-blowing speeds, and then we smash them into each other. The debris, the stuff that flies out from that collision, gets captured by these absolutely massive detectors. And it's by analyzing all that debris that we can start to piece together a photograph of what was inside and see how those fundamental particles actually interact. Okay, so you can probably imagine the math behind these smash-ups is just ridiculously complex. So to make it even manageable, physicists have relied on this really powerful simplification for a long, long time. And you can think of it like the auto mode on our cosmic camera. It gives us a decent snapshot for sure, but it's not the full picture.
Right, so this auto mode has a formal name. It's called the Eikonal approximation, and it's been a total workhorse for decades. I mean, absolutely essential. But as our experiments get more and more precise, its limitations are really starting to show. Basically, it makes three huge, simplifying assumptions: that the target is standing perfectly still, the collision happens in an instant, and that only the main, strongest force really matters. And this really gets to the heart of the issue. So first up, because of time dilation, that weird effect at near light speeds, the model just assumes the target particle is completely static, totally frozen in time. Second, because of length contraction, it assumes the collision happens in this infinitely thin, instantaneous shockwave. And third, it kind of just assumes that only the most dominant part of the strong nuclear force is even worth calculating. So the bottom line is that all these simplifications, while useful, give us a really incomplete picture. It's kind of like taking a flat 2D snapshot of what's actually a super dynamic 3D event. Yeah, we get the general outline, but all the fine details, all the depth, and the really subtle interactions, they just get lost in the blur. So, if auto mode is giving us this blurry picture, what's the solution? Well, it's just like with a real camera, right? To get that sharper image, we've got to switch over to manual mode and start fine-tuning the settings ourselves. And these adjustments, these manual settings, are what physicists call the Next-to-Eikonal corrections, or NEik for short. What they do is they systematically go back and relax each of those three big assumptions we just talked about, all to build a much more accurate and complete model of the collision. And this comparison really shows the upgrade perfectly. On one side, you've got Eikonal, the simple snapshot. But on the other, with NEI, everything becomes so much more realistic. The target isn't frozen anymore, it's dynamic. The collision isn't instantaneous, it actually has a duration, some depth. And we're not just looking at the main force, we're including all those subtle ripples. It's literally the difference between a quick cartoon sketch and a high-resolution photograph. Okay, so physicists have known about these manual adjustments for a while now, but actually applying them has been this huge, piecemeal effort. And that's what brings us to the real breakthrough of the paper we're talking about today. Because for the first time, it puts all the different pieces of the puzzle together. See, this isn't just one new calculation. The authors have built a whole comprehensive framework, a complete user manual, if you will. It lays out all the necessary mathematical tools. They're called propagators, which are basically the rules for how a particle gets from point A to point B during the collision. And this manual gives us everything needed to calculate what happens to both quarks and gluons at this incredible new level of precision. And this manual is an absolute treasure chest for physicists. It unlocks some huge things. I mean, for the very first time, it gives us the full, high-precision corrections for gluons. Then it combines that with their previous work on quarks, creating the first ever complete picture. It also just hands the entire community the building block formulas they need for their own research. And to top it off, it puts these new tools to work, actually calculating the production of specific particles in these collisions.
And this isn't just some isolated calculation off in a corner. This is a foundational upgrade to a major theory called the Color Glass Condensate, or CGC. The easiest way to think of the CGC is that it's our best description for this really weird, dense state of matter inside particles at extreme energies. It's like a super dense traffic jam of gluons. This paper takes that entire theory and just makes it way more powerful and precise.
Okay, so we've got a better theory, we've got sharper math, that's great. But why does this actually matter? What's the real-world impact? Well, this quote from the paper itself really says it all. The goal is to achieve reliable quantitative description of the experimental data. In other words, it's all about making our theories so precise that they perfectly match what our detectors are actually seeing in the real world. It's about closing that last critical gap between our predictions and reality. And this level of precision is absolutely critical. It means we can now take our theoretical predictions and compare them to the fire hose of data coming from places like the Large Hadron Collider and the Relativistic Heavy Ion Collider with so much more confidence. And every single time we do that, we are stress testing the standard model of particle physics. Because it's only by finding those tiny little cracks, those tiny disagreements between our super precise theory and our super precise data that we can pave the way for discovering brand new particles or even new forces of nature. So, when you take a step back, what's the big takeaway from all this? Well, this incredible work really gives us a glimpse into how science actually moves forward. It's rarely about one single eureka moment. So much more often, it's about the dedicated, painstaking, brilliant work of people just sharpening our theoretical tools, bit by bit. They're cleaning the lens, they're improving the sensor, they're writing a better user manual for our cosmic camera, all so that our collective picture of reality can become just a little bit less blurry. And that leaves us with a really tantalizing question. Now that we can take a much, much sharper picture of this subatomic world, what details that were previously lost in the blur are suddenly going to appear? What new structures, what new behaviors, or maybe even what new particles have just been waiting there in the shadows, waiting for us to finally figure out how to properly focus the camera?